So this video is going to pick up exactly where the previous one left off. So we were at a point where we could have, here's the code, we could have a pointer on an int variable, like called named data, okay? We could get the address of that int variable, put it inside the pointer variable, okay? And then we could use the dereference operator in order to follow this address, go at that address in memory, and read the value that's there. And that's what we did. We only did the reading part. So let me supplement what was in the previous video by showing you how the writing part goes. Knowing that I have the address of data inside P1, okay, can I use P1 to change actually the value inside of data? Yes. Dereference P1, but this time, instead of just using it like this as an expression, which value I want to look at, what I'm going to say is I want to dereference P1 and assign to that memory address a different value, for example, 9,999. So this is going to have as effect to change the value of data. Let's check that together. So I'm going to do a printf, one more printf here after doing this assignment. And this is going to be a printf of data again, just to show what is the new value. Let's save. GCC, run it. So originally data is 42, no problem. P1 contains this memory address. So this is a memory address at which the variable data is located. Address of data, confirmation. This is the same memory address. Then I try to dereference P1 and read the value that is located there. I get a 42. That's indeed what is stored inside of data. Then I try to dereference P1, but this time I use the dereference P1 on the left-hand side of an assignment operator. So I'm going to assign this value to the result of dereferencing P1. The result of dereferencing P1 is I go at that memory address and I find like an int there, and I'm going to assign 9,999 to that int. So the data variable has been modified by dereferencing P1. And when I display again the value of data, there we go, it has been indeed modified. So I'm going to leave that as an exercise, but what we did with P1 and P2 at the end of the previous video to try to generalize what if I have a pointer on pointer on pointer, we could do it as well with this kind of thing. Okay, we could like use, for example, star 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 P3 equal 9,999, and it would indeed triple the reference memory address and then change the value inside this variable. But right now, I just wanted you to see the pointers in action for the other aspect that we use them for, which is not only just reading, but also writing. And that's going to be enough for me to introduce the concept of restricting access to pointers. So the problem with pointers is if I have a pointer on a variable, I can do whatever to that variable. I can also modify my pointer. For example, if I have here data, I'm going to call it data and data2 equals 0. And what I'm going to do is I'm going to, at some point here, say, you know what, I'm done playing with P1 pointing to data. I'm going to reassign P1. So you can reassign a pointer, no problem. I want to put inside of it the address of data2. So now P1 points to data2. So if I want to show you graphically what this looks like, if I can, there we go. Here we are. Here's the whiteboard. So I have data here in memory, contains the value 42. I have data 2 in memory, contains the value 0. I have P1, which is a pointer. This pointer originally contains null, okay, on line 10. Then I assign to it the address of data, so the pointer points to actually the variable data. I display a bunch of stuff, and I'm going to follow the same convention here, called the memory address at which data is located alpha, and the memory address at which data2 is located beta. So I assign alpha to P1. Now P1 points to data. I can use P1 to read the value 42 from inside data. I can use star P1 to also change the value 42 inside P1. And then on line 19, when I assign, on line 23, when I assign P1 equal address of data 2, all I'm doing is I'm changing this here into data. I'm assigning the address of data 2. As a result, this pointer no longer points to data, but points now to the variable data2. And everything I was doing before, like reading the value of data2 using P1, changing the value of data2, of course I can still do it. Let me demonstrate. So here we're going to do, you know what, we're going to do the same thing that we did here, but we are going to do it for data2. And that should be enough to make my point. So I'm going to say, here's the content of data2. Here we are. Here's the content of P1, so it changed. Okay, now it contains the address of data2. To verify this, I'm going to display the address of data2 right after. And then I'm going to display the fact that I can access what's inside data2 using the reference of P1. And then I'm going to, again, dereference P1 this time to write something at that address, and then display data2 again here. There we go. So we have a little program here that illustrates pretty much everything we can do with pointer, reading, writing, etc. So between the previous video and this one, you'll be covered with all the basic operations. So let me scroll this up so we have everything we need on the screen, easily readable, accessible. And then I'm going to go back here. I'm going to compile, run. So let's follow the trace together. So this part here didn't change, okay? Data is still 42. P1 contains this address. This is indeed the address of data. I use P1, dereference P1 on line 17. I access the content of data. Then I use dereference P1 on line 19 to assign a new value to data, which is displayed on line 21. And then we switch our attention to data2. Data2 starts at 0, no problem. This is the pointer P1 after I assign P1 equal ampersand data2. So after line 23, this is what the address is, and it's different. Okay, so this is the address of data. This is the address of data2. To make sure that that this is indeed the case, I display here the address of data2. You see that it matches what's in my pointer right now. After that, I use P1 to read the value inside data2. It's still a 0, no problem. And then I use P1 on line 30. Let me scroll down a little bit to, again, dereference that memory address, but this time I change the value located at that memory address, 9,999. And when I display again data2 on line 32, you see that it has been indeed updated. Okay? All right. So this shows you that once you have a pointer on a variable, you can do a lot of damage. Okay, you can go and change the value of that variable. You can read memory addresses in memory. You can write memory address in memory, and that's actually the #1 problem with pointers. If you put the wrong memory address in a pointer, and you can do that. Okay, this is going to happen to many of you. You put the wrong memory address to a pointer. The pointer is considered corrupted. Okay, now it points to a zone in memory that has nothing to do with what you wanted it to refer. And then you can read, you can write. This poses like safety for the code execution and security issues. Okay, so we have a tool that allows us to kind of control a little bit what can be done with a pointer. When you declare your pointer, by default, your pointer can be modified. This is what I did here with P1. At some point, I changed my mind and I said, you know what, P1 on line 12 was the address of data. I changed my mind. P1 is now going to be the address of data2. Okay, it's going to contain the address of data2. So by default, you can change the value inside your pointer. And you can also change the value that you are pointing to. So that's why I was able to do star P1 equal 9,999. And here again, star P1 equal again 9,999. Okay. by dereferencing P1 and writing this value, I have access to the int actually that is being referred by my pointer P1. Okay, so these are the two things that we are going to be able to lock down. Whether we can change the pointer itself, and whether we can change what is at the address that the pointer contains in memory. To do that, we use the keyword const. So if I put the keyword const here, I read my declaration right to left. P1 is a pointer on a constant int. So what I did lock down here, what I did protect, is actually the area of memory that is being referenced, that is being pointed to. Okay, the area of memory which address is in the pointer. I said it's a constant. You cannot modify it. So if we try to compile this, let's go here, GCC, assignment of read-only location star P1 when we do on line 19, star P1 equal 9,999. So this is the first time we have been using star P1 to read value, like here, okay? But this is the first time on line 19 where we're trying to assign a value at the memory address stored in P1. And the compiler catches it because we said, no, you cannot modify what is being pointed by P1. And this is exactly what we are trying to do here. So this is actually caught on line 19, this is caught on line 30, so the compiler realizes every time we are trying to dereference a pointer to write something in memory, if we declare that pointer as being a pointer on a constant zone of memory, then it's not going to work. So that allows us to prevent somebody from using the pointer P1 to actually go ahead and modify the variables data and data2. We can read, we cannot write. Okay, awesome. What about changing actually the pointer itself? Okay, like reassigning P1 to being the address of data2 after it was the address of data1. We can prevent that too, no problem. Okay, what we need to do is we need to use again the const keyword, but we need to put it elsewhere in our declaration. So we need to insert it here between the name of the pointer and the star operator here that allows us to declare P1 as being a pointer on int. So we read again the declaration from right to left. P1 is a constant pointer on an int. So the difference between a pointer on a constant int and a constant pointer on an int is that the object of the qualifier const is actually the pointer itself this time. Okay, pointer on a constant int. What is constant is the memory that we refer to. Constant pointer on int, the int can change, but the pointer now is a constant. So if we write this, now we are locking down the ability to change actually P1. So let me save. Let me compile again. And now it's telling me similar message, okay, but it detects a problem on line 12 this time and on line 23. This is where we try to assign values to P1, okay, so the initial value, the initialization here is okay, but then when we try to change the value of P1 here or here, then the compiler tells us you cannot change the value of P1. P1 has been declared as a constant pointer, okay? Because of that, you cannot modify the address inside P1. So we are stuck with P1 equal no, which is not going to be super useful, right? But that shows you how you can actually make it so that the pointers, once it has been set to an address, so if I was setting it here, for example, to the address ampersand data, okay, and therefore I don't need that line anymore. If I was doing this, then let's say compile, I would be able to set its initial value to be the address of a variable, but then I would prevent the code from being able to modify it here afterward, like on line 23, for example. Okay? All right, so I can make the pointer a constant. I can make what is pointed to a constant to protect from the write operation, the change operation, right? Can I do both? Absolutely. So we can, it's not going to bring anything new when we try to compile, but we can say, I want a constant pointer. So read always right to left. P1 is a constant pointer. So I should remove that space here just to make it more readable. Is a constant pointer on a constant int. And that's it. Okay? So if I do this, well, then it's completely locked down. That means I cannot modify the value of P1, the value inside of P1, that memory address. I cannot modify it. I cannot even dereference P1 to go modify what is at that address, the int value that is at that address. See, here I'm prevented from actually dereferencing and modifying the int value that is being pointed at. Here I'm prevented from actually changing the memory address inside of P1. And here I'm prevented again from dereferencing the memory address and going to change the int value that is at that memory address. Okay, so it's complete lockdown. So there are really four possibilities. Okay, you have a pointer, a non-constant pointer, I should say, on a non-constant data type, like an int, for example, or a double, or a float, or whatever. And then you can have a constant pointer on a non-constant data type, a non-constant pointer on a constant data type, and then the total lockdown is a constant pointer on a constant data type. Okay, and we covered the four examples with this little program here. So this is useful. This is relatively useful like that to be able to secure a little bit your code, prevent any part of the code to do anything in memory wherever it wants. So that's fine, but that's really going to shine when we start using pointers with function. And this is the main topic for this video. For this video, we are going to try to apply what we learned so far about pointers, including the use of the const keyword, to mix it in with what we know about functions. So right now, whenever we use a function in the C programming language, we pass arguments by value. Okay, so when you call a function, for example, let's do a function called modify, and I'm going to say modify data, for example. Okay, and we have been playing with that, and we've been doing the swap functions as well. So you know exactly where I'm going with that probably, but I'm going to rebuild the example for you. Okay, so I'm going to say that the function modify takes an int as parameter, returns nothing, and at the end of the main, after the end of the main actually, I'm going to say that the code for modify is you give me a value, I'm going to call it n, and I'm going to set n to, I don't know, 99? Why not? All right, so what I would like to be able to do, I'm going to erase all of this because we don't need it. It's just going to muddy the water. What I would like to be able to do here is I would like to be able to start with data equals 42, then call modify on data. So data is my argument. And the mistake that a lot of people make here is to say I'm passing the variable data to the function modify. And therefore modify can modify the variable data from the main under the name n. It's like n and data are two aliases of one another, right? And you know by now this is not at all how it works. Here's how it works. When you call modify with data, this is an expression. This expression is evaluated. So how do you evaluate something that is just the name of a variable? You look inside the variable, you take the value. So this is like if I was calling modify with the value 42. So the arguments always end up being evaluated into values. Then those values are copied inside the parameter. But here's the deal. The n parameter here for the method, for the function modify, lives in the activation record of that function. And it only exists while the function modify is being executed. It's going to be created on the fly, initialized to 42, which is the value I'm passing as argument. Then I'm going to modify it and set it back to 99. When I complete my function here, I'm going to return to the main, and n goes bye-bye. And what am I left with? I'm left with data here that has never been modified. Okay, so we've seen already that. If you need a refresher, I really recommend that you watch again the video where we cover this. Okay, but now I'm going to add a little bit to that. So now what I want to do is I want to use what I learned about pointers. The part that really interests me is that if I give a value, which is the address of a variable, and store it inside of a pointer, if I take, I should not say give, if I take a special value, which is the address of the variable data, and I put it inside a pointer variable, then I can use that pointer variable to access data and modify it. Okay, we've done that. This is exactly what we did in the previous video. Here's my pointer ptr equals address of data. Okay, and if I write star ptr equal 0, then data is going to be equal to 0. Okay, so I've done that, but I've done that inside the same function where I define my variable data. Do you see how this connects to parameter passing? What if I said I'm going to take the address of data, but instead of assigning it to ptr, I'm going to pass it as an argument. So again, my argument is this expression. This expression is evaluated by taking the address of the variable data, and that's the value that I'm going to pass to my function. So this is going to be 0x 7fff. I don't remember what was the address that we used before, but there's going to be a bunch of hexadecimal digits here, okay? So I'm going to pass the address of data to my function. My function is going to receive this address. What do you use to store addresses? You use pointers, okay? So now I'm saying that my parameter n, and I should call it something like nptr, okay, to remind myself that this is a pointer. My parameter nptr contains actually the address of a variable from the main, this one right here. Okay, what can I do when I have the address of a variable inside a pointer? I can dereference our friend nptr and say I want to modify whatever is at this address. Let's take a look at how this is going to work here. I'm going to printf before data is %d, and then I'm going to call modify, and then I'm going to say after data is %d and display it. Okay, let's save. So need to get rid of some errors here, like I forgot to update here my my prototype. So there we go. I changed the type of my parameter. I need to update this. gcc main.c, error out. So line 9, data is declared and is assigned initialized with 42. Okay, so data contains 42. Before data is 42. No problem. I understand this. This makes sense. Call modify ampersand data. So ampersand data is going to be evaluated into the address of the variable data. This address is actually copied inside the parameter called nptr. Okay. Then I dereference nptr. I set to the memory address that nptr refers to. I set the value of that int to 99, and I exit. When I exit my method, my function modify, nptr doesn't exist anymore, but the damage is done. I use nptr and the address that it contains to follow the reference to that memory address, which is the memory address of data. So I went and located the data variable from the main by dereferencing the pointer, and I changed what was inside of it. So the damage is done. This variable has been modified. From inside this function, I was able to modify a variable that is from another function, in this case, the main. But it could be any other function that called my function, okay? If you give me the address of something, I can go ahead and modify whatever is stored at that memory address. And so when I display again in the main after the call data is data, well, you see that it has been indeed modified. This is awesome. That means that now I can modify, I can pass, it's like I can pass a variable as parameter to a function and have that function modify the content of this variable. This is what everybody refers to as passing parameters by reference, okay? Because we pass a reference to a variable and we allow the function to modify this variable. But really, if you are asked, so how many different ways are there in the C language to pass parameters? Is there a pass by value and then a pass by reference? It's a trick question because, yeah, in a way we do have a pass by value, pass by reference. But if you think about it a little bit, all there is really is pass by value. It's just that sometimes the value that we pass as an argument is a reference. It's a memory address. And when that value is a memory address, we can get it, receive it inside a pointer parameter, a pointer variable, and we can use that pointer parameter with a dereferencing operator to read what is at that memory address or to write what is at that memory address. Let's do a quick stack diagram here so that you have the complete, analog example from what we had before with the swap method, okay? I'm going to trace pretty much what's happening once more in this code, but I'm going to do it with not a trace table, but just with a stack diagram, actually, a simplified stack diagram. So I start executing the main. I have the variable data. Data contains 42. So that's line 9, sorry. Line 10 simply displays on the screen the content of data. Then I call modify. So the expression ampersand data is going to be evaluated to be the value of the address at which data is located. So we're going to keep using those Greek letters for memory address. Let's say that the variable data is located at memory address alpha. When I call modify ampersand data, okay, this whole thing here becomes alpha. It's evaluated and yields the value alpha. So this is the value alpha that I'm passing as parameter, okay? This value alpha is actually stored inside NPTR. That's the parameter. It's a, it's a pointer data type, so that it's meant to hold an address, no problem, which means that NPTR now refers to the variable data. And when I execute on line 21 star NPTR equal 99, this is NPTR, star NPTR at dereference, and I write 99 here. So that's one way to understand what's happening, okay? And then my function completes on line 22, NPTR goes away, but the damage is done, I modified data. That's one way to understand it. The more accurate way to understand it, it's going to be the same meaning, okay? But I just want you to get used to different models in your mind of what's happening in memory. Another way to look at this is to say, okay, I have the program's execution stack. Okay, remember our good old stack here. This is the activation record for the main. So main activation record, okay. Inside of which, well, I have a few things, but I have of interest data, okay, the local variable data, which contains 42. And it is located at memory address alpha. And then I call modify ampersand data. So I'm going to pack here, this is the activation record for the main. I'm going to now have an activation record for my call to the function modify. All right. Inside of modify, I have like return address, etc. But then I have nptr. Okay, this is my parameter, my pointer. And this nptr is going to receive the value alpha, which means that technically nptr points to data, okay? And when I do star nptr equal 99, I follow this green arrow, I dereference the memory address alpha, I go to the memory location alpha, and I write 99 right here. And then when I complete execution of the function modify, the activation record for modify goes away. So all of this disappears, goes away, okay? And what I'm left with I'm left with the activation record of the main function, which contains still the variable data, but that variable, sorry, that variable has been modified. Okay, so we took different looks here at what's happening, but all of those perspectives are complementary of one another. Okay, they all just show the same thing. Now that we have that out of the way, let's talk a little bit about Scanf. So every time we have been using Scanf, for example, if I want to read here printf give me a value for data. Okay, if I want to read a value from the user and store it in the variable data, I would say I want to read, for example, an int, and I want to store it inside of data. So that ampersand that I ask you to put in front of data, what is the meaning? This is the address of operator. That means that I'm taking the address of the variable data, and this is this address that I pass as an argument, as a value, to the function scanf. The function scanf on the receiving end is going to declare its second parameter as being a pointer on int, and it's good, well, it's not exactly true, but for the purpose of this video, it's going to be good enough. It declares the second parameter as being a pointer on int, so that it may receive actually the address of an int variable somewhere in memory, and it's going to dereference that pointer to be able to write inside that variable. So really, when we said, every time you call scanf, you put ampersand and the name of the variable, and that allows scanf to write inside that variable. This is exactly what we did. Okay, we passed actually an address to a pointer parameter, and that pointer parameter was used to dereference, just like we did here inside scanf. Okay, it's used the same way that we used it inside of modify, pretty much, to dereference to that address and change a value therein. Okay, except that here, of course, we read from the user and we put the value in there. So if I run this, let me make sure that I save my file first. gcc a.out, give me a value for data 555. There we go. Before data is 555, after data is 99. So we could say that there is this data variable in the main, and we passed it by reference to scanf. Well, you know the truth, we pass a value actually to scanf, which is just so happens to be the address of the variable data. We passed this to scanf, which allowed scanf to modify the content of data. It put 555 inside of it because that's what I typed. And then we passed again, to use the lingo, by reference, data to modify, but you know that what that means. That means we pass by value actually, and the value was the address of the variable data, which allowed the function modify to also modify what was inside data using its parameter, pointer, and ptr. Okay, so we modified twice pretty much this stuff here. So that kind of like remove a little bit of the mystery of scanf and its syntax and why do we use that ampersand operator. So very good. The next thing we need to talk about, and it's going to be a segue into the next topic as well. The next thing we need to talk about is what happened when we try to read strings of characters from the user. Okay, I'm going to keep things on the screen here so that you have them side by side, you can compare. Okay, at some point I said, I want a string, and I want a string that can hold, for example, 100 character, and I declared it as an array of 100 character. So an array of 100 character can hold 99 letters, symbols, whatever, and then the last element is reserved to be that \0 character that marks the end of string. Okay, so I use that, and I use that also to store strings inside a character up to a size of 100. The way that I did it is I said, for example, give me a string. Okay, and the format specifier for string is S, and I said here, well, you know what, I'm going to read a string up to size 99, so up to 99 character, and then add that end of string character that will fit perfectly in my buffet, but that's the maximum that I allow. And then here, if you notice in the previous videos, I did not put %str. I simply put str. Why is it? So first, let's make sure that this works, right? And then I'm going to say here, printf, you typed, and then I'm going to display %s here, and my string. Okay, so let's make sure that this works first. Compile, run. Give me a value for data, 555. Give me a string, 555. You type 555 before the data is 555, etc. That part didn't change, okay? So I was able to read a string of up to 99 characters. I was able to store it in an array that is oversized for that string. It has up to 99 characters plus the end of string marker. And here I use what, like 4, 12, 14 characters. That's it out of it. 15 with the end of string marker. So I was able to process my string. I didn't have to follow the same rule. So there is an exception here. Where is that exception coming from? Well, that exception is coming from the fact that when you declare an array in C, the vast majority of the time, or I should say for the most common use cases, your array can be seen as a pointer. It's a memory address. Okay, when you have an array like this, so I'm going to clear some space here, and we're going to take a closer look at str together. Okay, when you declare str, the name str is used to locate the first element of your array. So this is your array in memory. Sorry, I cannot draw a line vertical, apparently. It has 100 elements, so start at index 0, 1, up, keep going. And then this is going to be element index 99. Okay, there we go. So we have at a certain memory address, which we are going to call to the original alpha. At memory address alpha starts actually the first element out of a series of 100 elements. Each of them is of type char. This is a char, this is a char, this is a char. Okay? So all of those elements are of type char. There's 100 of them. All we need to keep track of to know where that array is the address of the first element. Well, it's not exactly true. We need the address of the first element, and then we need to remember that inside this array we have 100 elements. Okay? So two things. An array is really that. An array is the address at which the first element can be found. This is this guy. And then somewhere else, you remember that you have 100 elements, so that allows you to write a loop, for example, that goes between 0 to 99. If you don't remember how many elements you have, well, you take a chance that one day you are going to try to access element str index 200, and that's going to cause some mischief, okay, because you're accessing technically memory that is somewhere here, way past the end of the array, okay? So yeah, you need to keep track of those two information. One of them is external, the number of elements. You keep it as a constant here in your code, or you put it in a constant variable, or a symbolic constant, like we've done actually in the previous videos. And the second part of the information, the address where the whole array starts, well, it's given to you by the name of the array. So when you use the name str, you are using actually a name that is aliased to a memory address. So it's not exactly the same thing as a pointer, right? A pointer is a variable, like for example, we could have a variable p here somewhere, okay, which is a pointer, and that pointer could contain the memory address alpha, and therefore that pointer would be said to point to the first element of your array. How would that look like in code? Well, we could write something like char star ptr equals, and I want to say the address of the first element of the array str. address of element index 0 in str. I could write it like this, okay? As a matter of fact, I'm going to write it two different ways. So let me initialize to node, and then let's do first method. Okay, I'm going to write ptr equal the address of the first element of the array. Second method, ptr equal str. Because I said that the name of the array was actually an alias for the address. So when I assign str to ptr, I'm not assigning the whole array. Str is going to be understood as being an alias for the address of the first element. I'm assigning the address of the first element to ptr. What is ptr? A pointer. Okay, so are we assigning apples to apples here? ptr is a pointer on a char, on one char element. I'm putting the address of the first element of the array, one char element, into ptr. Match. It's working just fine, right? So I can write this. Let me make sure that it compiles so that I don't mislead you. There we go. So we don't need to go through that again. There we go. The code is still working. But the interesting part is that now we have this pointer ptr, and we can use that pointer ptr to do things such as, for example, star ptr equal. I'm going to change the first character, and I'm going to say the first character is now an uppercase Q. No matter what I type, okay, I'm going to change the first character to a Q. So I'd better do that actually after I am done reading the string to start off with. So I'm going to read the string. There we go. And then I'm going to use the shenanigan here to modify the first letter of the string. And then I'm going to display again what was typed. Let's see if that works. GCC, a.out. Give me a value for data. We could comment that out. We're not using it anymore. And I'm going to say A, B, C, D, E, F, G. All right. And you typed Q, B, C, D, E, F, G. Okay. Similarly, I could replace by any character, including \0. That's interesting, because that's going to shorten my string. It's going to make it an empty string, actually. Let's take a look at how it works. Okay. Give me a value for data, 555, A, B, C, D, E, F, G. You typed nothing. So what happened here exactly? Let's go back to the drawing board, okay? So, well, we have almost everything we need here, so I'm going to clear up a little of the board. Here's what happened. When I first read A, B, C, D, E, F, G from the keyboard, okay? I didn't mean to delete all of that, but let's go ahead and redo it cleanly, okay? All right. When I read A, B, C, I'm going to stop at D. Okay, you get the point. When I read ABCD, if I type ABCD, enter on the keyboard, okay, here's what happened. At index 0, the character A was stored. At index 1, the character B was stored. At index 2, the character C. At index 3, the character D. At index 4, the character end of string, \0. And even though there were more slots available in my array, okay, up to index 99, I didn't use the rest of the array. So there could be garbage in it, I don't care. Then what I did is I set my pointer to contain the address of the first element of the array str. Or I set the pointer to str directly, which is exactly the same thing, okay? Those two lines here, line 19 and line 21, completely equivalent. And then I said star p equal \0. So what I did is I modified this element here, and I replaced the A character by \0. What happened when I tried to display that string? Well, I gave str to printf. Str is the address of the first element, so that's how it works, right? To display a string, you tell me where the first character of the string is, and I'm going to display that character, then the next one, the next one, the next one, the next one, until I meet the end of the string, which is identified by the character, the special character \0. But oh, look at what happened here. The \0 was the first character. That's why I have an empty string. If I wanted, I could have said, hey, I want to make p point, for example, to the character index 2 of my string, or 3 or 4, and then put a backslash 0 here. I forcefully insert a backslash 0 somewhere in the string, okay, in my array of 100 elements, before the first occurrence of backslash 0, and suddenly I shortened my string. So we are going to talk more about that. Again, we are going to do a lot more things with strings. But right now, I'm just going to illustrate that second scenario that I just mentioned. I'm going to say here that ptr is no longer going to be equal to just str, okay? But ptr is going to be equal to the address of str index 3, the fourth character, okay? And to show that in action, I'm going to save it. I'm going to go here, compile, run, give me a value for data. Really should get rid of that. And then A, B, C, D, E, F, G. So here's what happened. A, B, C, D, E, F, G backslash 0 was stored in my array str. Then I went and I found the element at index 3 in str. That was A is index 0, B is index 1, C index 2, D is the element index 3. This is the fourth one. And what I did is I put the address of that element in the array, the character D, where the character D is located. I put that in my pointer, and then I use my pointer, dereference my pointer, to be able to actually change the content of that area of memory, and I replace the character D by the character backslash 0. As a result, the next time I told printf, hey, display the string str, it looked at the address of the first element in that array. Okay, this is what str is. It found the character A, displayed it. Then look at the next character, B. The next character, C. The next character was now a backslash 0. End of string met. I stopped displaying the string. Okay? All right, so I'm going to leave that as an exercise, but if you understand what we're doing here, you should be able now to write a swap function that's capable to take as parameter, as argument, the address of two variables from the main, for example, and use pointer dereferencing to swap them. Try to do that. If you bump into any problem, come to office hours, okay, post on Piazza, forum, you know the drill. And let's try to use that as a sort of a checkpoint. Okay, in order to make sure that you understood the material from this video and the corresponding reading assignment from the textbook, try to write that swap method by yourself without looking it up in the textbook, because it's going to be presented later in this chapter. Okay, and if you need some help, you know where to find us. All right, I'll see you in the next video.